All right, folks, now we're going to look at this linear transformation here, which has the associated matrix A, and our task is to find the associated eigenvalues and eigenvectors of that matrix for that linear transformation. So I encourage you also to look at the 3 blue, 1 brown video that goes through a visualization of this, but we're going to find this algebraically by working with the characteristic equation that we looked at in the last video. So I think of the characteristic equation as a tool for finding the eigenvalues. So we can go ahead and set that up. We know what A is, we know what I is, and so then we're going to be taking the determinant of matrix A, which is 3, 1, 0, 2, minus some unknown lambda, times the identity 1, 0, 0, 1. And when we do that, we end up with the determinant of the matrix 3 minus lambda, 1, 0, and 2 minus lambda. Folks, if I did that too fast real quick, if we take lambda times the identity matrix I, we'd have lambda times 1, 0, 0, 1, which would give us 1 times, lambda times 1, lambda times 0, lambda times 0, and lambda times 1. But of course, that just gives us lambda, 0, 0, lambda. So another way to think about it is when I multiply the identity matrix by the scalar lambda, I get lambdas along the main diagonal and zeros everywhere else. So now we can go ahead and compute the determinant. We know how to compute any n by n determinant, although sometimes it's more difficult to do than others, but since this is a 2 by 2, it's not too bad. The determinant of this matrix would be the A entry, that's this first entry, times the D entry, so minus 2 lambda, minus the B entry times the C entry, so minus 1 times 0. That needs to equal 0. And if we FOIL this out, we will get 6 minus 3 lambda minus 2 lambda plus lambda squared minus 0 equals 0. Or now we can write this as a polynomial in terms of lambda in expanded form, and we end up with lambda squared minus 5 lambda plus 6 needs to equal 0. So folks, this is sometimes called, on the left-hand side here, this is called the characteristic polynomial because it came from the characteristic equation. Notice that it will always be a polynomial in terms of lambda, and so we can go ahead and find the zeros of this polynomial. In this case, it's just a quadratic, and it factors as lambda minus 3 times lambda minus 2 equals 0. Careful, we could see that up above, we could see that earlier, but that was only because this term right here simplified to be a 0, which usually won't be the case, or which often won't be the case. So this gives us 2 eigenvalues. The eigenvalue lambda equals 3 and lambda equals 2 are 2 eigenvalues of the transformation T and its associated matrix A. Let me maybe put that in parentheses. So once we find the eigenvalues, what do? Well, in terms of this question, we're partway done. We found the eigenvalues, but we're also tasked with finding the eigenvectors. So how do we do that? Well, if you go back to the derivation of the characteristic equation, we had somewhere in there a line that I said, pay attention to this, where we had the expression A minus lambda I, that matrix, times the supposed eigenvector V needs to equal the 0 vector V. Okay? This is the equation that we're going to use to find the eigenvectors. So let me just emphasize this. I use the characteristic equation. I think of that as a tool or an equation for finding the eigenvalues, whereas I use this equation right here for finding the eigenvectors once I've found the eigenvalues. So it's really important to keep in mind the differences between these two equations. This is a real valued equation where we've got a 0, the number 0 on the right hand side, and when we go through to solve it, we end up with a polynomial set equal to 0. This equation right here, this equation is a matrix equation, and we're going to have to solve that as a system of equations the way we have using either Cramer's rule, multiplying by the inverse if the corresponding matrix is invertible, And the best way to do it is through the Gauss-Jordan elimination method. So let's go ahead and set that up for this problem. Let's pick one of our lambda values. Let's pick lambda is equal to 2, and let's find the corresponding matrix equation. So this will be, let's see here, we had matrix A was 3, 1, 0, 2, I believe. Let me double check that. Yep, 3, 1, 0, 2, minus, and here we're picking the value 2 for lambda, times I, 1, 0, 0, 1. And we're going to multiply all of this by our unknown vector v, and we want this to equal the 0 vector. So cleaning up that matrix on the left-hand side and going very slowly, because this is where it's easy to make a mistake, we'd have 3 minus 2 for that first entry, 1. Then we have 1 minus 2 times 0, well, that's still 1. Then we'd have 0 minus 2 times 0, well, that's still 0. And then we'd have 2 minus 2 times 1, that's 2 minus 2, or that entry is 0, times our unknown vector, which will now break into components of v1 and v2, and we want that to equal the 0 vector in R2. Well, in R2, the 0 vector is the vector 0, 0. So now we've got a system of equations, or a matrix equation that we can solve, and let's use Gauss-Jordan elimination. So we take the columns of the coefficient matrix 1, 0, 1, 0, and we're going to adjoin that to 0, 0, and then we're going to resolve this through Gauss-Jordan elimination. Well, this is actually already in RREF form. There's nothing more we can do, and we can go ahead and read the solution from this. This says that V2 is free, and that V1 plus V2 has to equal 0, or that V1 is equal to negative V2. Okay. Often for the case when you go to find the eigenvectors, we will have, unless it's kind of an unusual circumstance, we will have at least one free variable that we find when we go ahead and solve the corresponding system. So there's nothing unusual there. In fact, it's somewhat to be expected. So because V2 is free, let's pick a value for, we're just looking for an eigenvector here. We don't have to find all eigenvectors. We'll do that when we give the eigenspace. So let's just go ahead and pick V2 is equal to 1. As a consequence of that, because V1 is equal to negative V2, we get that V1 is equal to negative 1. So an eigenvector of lambda equals 2 is the vector negative 1, 1. Okay. Careful, folks, when people go to find eigenvectors, the solutions to this is not unique. So somebody else might say, I think the answer is 3, negative 3. And you'd have to recognize that, yes, that these two eigenvectors are equivalent, and one is just a scalar multiple of the other. So be careful with that when you're looking at somebody else's solutions. You might both be right. It's just one answer is a scalar multiple of another. I usually, when I'm given an option to pick a value, I usually pick 1, unless that choice will cause me to have fractions in the statement for the eigenvector, in which case I'd multiply that by however big of a factor I need to avoid fractions. We'll see that in some later examples. Okay, so we just saw that, in quick summary, we went ahead and solved the characteristic equation, and we found two eigenvalues through that characteristic equation. Notice that that broke down to eventually solving a polynomial for lambda. So we use the characteristic equation as our tool for finding the eigenvalues. Then we select each one of the eigenvalues. We've only done this for lambda equals 2 so far. And then we solve this equation for the unknown vector, which will be our eigenvector, an eigenvector associated with that particular eigenvalue. Okay, so let's pick our other eigenvalue. Let's pick lambda equals 3. So when we do that, we still have, let me just rewrite this. We have a minus lambda I times our unknown vector v needs to equal the 0 vector. So we'd have 3, 1, 0, 2 minus 3 times 1, 0, 0, 1. That's 3 times the identity. That's our eigenvalue. 3 times the identity matrix times our unknown vector v needs to equal the 0 vector. When we clean this up, we end up with, let's see here, 3 minus 3 times 1 is 0. 1 minus 3 times 0 is still 1. 0 minus 3 times 0 is 0. And 2 minus 3 times 1 is negative 1. That's our matrix of coefficients times v1, v2, and we want that to equal the 0 matrix 0, 0. In this case, when we go about putting this into RREF form, notice we would take 0, 1 adjoined with 0, 0, negative 1 adjoined with 0. There's not really a whole lot we can do to put this into RREF form. We could rewrite the we could divide the second row by negative 1, so that gives us 0, 1, 0. And then we could go ahead and multiply negative 1 times row 2 and add it to row 1, which gives us 0, 0, 0, 0, 1, 0. And we said, hey, whenever you end up with a row of all zeros when you're doing Gauss-Jordan elimination, you go ahead and just, by convention, you put that at the bottom. And so this is how this row reduces. Okay. So notice that in this case, we only, again, like before, we got only one pivot column. Okay? So notice that V2 has to equal 0 in this case. As we read across these equations, that's V1 plus V2 has to equal 0. Yep, so V2 has to equal 0. And we see that V1 does not have a pivot column, so V1 is free. So we can pick any value we want for V1. I recommend picking 1, but you could pick any other number. Okay. So 4 lambda equals 3, an eigenvalue, an eigenvector is the vector 1, 0. What does this mean? Well, at this point we're just concerned with the mechanics of actually computing the eigenvalues of an eigenvectors, but I encourage you to look at the 3 blue 1 brown video for a visual demonstration of what we just found. Essentially what we're saying is that when we do this linear transformation, most vectors are going to get mapped somewhere else under this linear transformation. However, vectors that are of the form negative 1, 1, those vectors will only get stretched by a scalar. Namely, they'll get stretched by a factor of 2. And vectors of the form 1, 0, or any multiple of that vector, will get stretched by a factor of 3 under this linear transformation. Folks, we're going to do another more challenging example in the next video, but please let me know if you have any questions on this.